So now we are in the part 3 of the Rayleigh-Plateau instability analysis. In the previous lecture, for a varicose mode, we derived this equation D, which is the modified Bessel's function for the radial velocity u of r. And we also have a relationship between the pressure term and the radial velocity, as well as the axial velocity W and pressure. That's B and C. I've written these equations in a slightly different format. Now, let's look at this equation D. The solutions are already written down in terms of the modified Bessel functions. Now, C1 and C2 have to be determined using the boundary conditions. The first condition is that, notice that K1 of the Bessel function K1 diverges as x goes to 0. So in other words, as you go towards the center, that is, for us, K goes to 0 is equivalent to R going to 0. So as you go to the axis of symmetry, this Bessel function diverges. So therefore, the second term in the general solution in equation E diverges, and that's undesirable. Therefore, I can make a simple statement that since K1 of KR goes to infinity as R goes to 0, we require C2 to be 0 to suppress this unphysical growth. Okay. Therefore, now I have got U of R as C1 I1 of KR. Right. I have got the radial velocity up to an arbitrary constant. Okay. We want the equation B. If you see this equation, the pressure gradient is related to the radial velocity. From equation B, we know dP by dr is minus rho omega capital U of R. This is nothing but minus rho omega C1 I1 of KR. That's dP by dr. And therefore I get P of R would be obtained by integrating dP by dr, and this would be minus rho omega C1 integral of I1 of KR dr. Right? But we use a well-known result. Or a well-known relation, which is the derivative d by dx of I0 of x is equal to I1 of x. Okay, if you remember the modified Bessel's equation, we had this argument n. So n equal to 1 was the solution that we used for getting the general solution for u of r, the radial velocity. But you can have other values of n. So you have Bessel 0 as well. I0 as well. So we have the derivative between this. So the reason I'm using this relation is you can anticipate already with this where I'm going with this. So integral of the left hand side will just give me I0, and the right hand side I'm going to get integral of I1 of x dx. Right? So that's a result, that's a relation. So I'll go back to black ink again. Let x become KR. Therefore, dx becomes K times dr, and d by dx becomes 1 by K d by dr. And therefore, now I have P of R simply becomes minus rho omega C1. I1 just becomes 1 by K of I0 of KR. So I've actually got P of R as well. Right? And using the last equation C that we have, we have now a relationship between the axial velocity W and pressure, and that relationship goes like this: Ik by rho times omega of P of R, right? And what do I have now? If I substitute the expression for P of R, I get I C1 I0 of KR. This is the expression for W, right? So in summarizing, what do I have? I have U of R is C1 I1 of KR. W of R is IC1 I0 of KR, and P of R is minus rho omega C1 by K I0 of KR. Notice that W has an I sitting in front. If you were to write it as an argument in terms of a phase, I could be replaced with e power I pi by 2, and that will be like quarter wavelength, just as we had anticipated. So the next step is to get the boundary conditions. Is to invoke the boundary conditions at R equals capital R of Z comma T. Note that we have already invoked the boundary condition at R equal to 0 to get C2 equal to 0, right? So we have a couple of boundary conditions. What are the boundary conditions? Let's look at the first one. So I have an interface like this. I'm only going to draw one side of the interface. I have a bulge. So if I'm at any arbitrary location where the radius is R, I have the first one condition that I have is called the kinematic condition. What's the kinematic condition says? It says if you are sitting on the interface, then if the radius is changing back and forth, you are literally equal. The rate of change of this radius would just be equal to the velocity at that point, right? And what velocity will that be? If the radius is increasing, you are changing in the radial fashion. So therefore, the rate of change of radius is exactly equal to the radial velocity at that location. So in other words, del R by del T will simply be the radial velocity at R equals capital R. Okay. We can make one additional simplification. This can be written as UR at R equals R0 plus small terms. These are basically Taylor series expansion. In other words, what I'm trying to arrive at is that you originally have an unperturbed interface at a distance of R0. If the perturbation amplitude is small, if epsilon is very small, then the boundary condition should ideally be on the interface, which is at R equals capital R. But the velocity at R equals capital R can be expanded about R equals R0 using a Taylor series expansion. And what you're going to get is subsequently you're going to get the, remember R is equal to R0 plus epsilon e power omega t plus I kz. The small terms that we are talking about will involve a product of the amplitude of the amplitude of the radius, that is epsilon in this case, multiplied by the derivatives of the velocity with respect to r. Therefore, it will be a product of two perturbations, a radial perturbation and a velocity perturbation, and the product of the perturbations would be small. And therefore, the boundary condition is not applied at r equals capital R, but at r equals r naught, which is on the undisturbed interface. Okay. So the left hand side in this case just simply becomes del r by del t becomes epsilon omega e power omega t plus ikz. This simply becomes capital U of r at r equals r naught e power omega t plus ikz. And therefore I simply get epsilon times omega is capital U at r naught. And what is the capital U of r naught? We already got the expression for capital U, which is C1 I1 times kr. So implies epsilon times omega will be C1 I1 of k r naught. That's the first condition. The kinematic condition is just a geometrical condition. It says that if the radius is bulging out, you need to have fluid filling in that void. Okay, fluid has to be pushing in at the interface to bulge out. At the same time, if the radius is actually shrinking, it's squeezing at some z location, the fluid has to move away and give space for the interface to shrink. Okay, this consistency condition at the interface is the kinematic condition. It is closely associated with mass balance as well. Okay. Now, having introduced the geometric constraint, now let's introduce dynamic constraint. What is the dynamic constraint? It is the normal stress balance at the interface. What is the normal stress balance? It says delta P will be gamma times 1 by R1 plus 1 by R2. Okay. Where is this coming from? This is just coming from the normal stress balance that we had derived on the inside and outside. But the only difference is that n dot capital T dot n, the term that we had, the stress tensor will just simply reduce to pressure because we have no viscosity both inside and outside. Okay. Now, first we have to understand what is this R1 and R2. For this, I'll draw an slightly exaggerated interface. So let's consider an interface which is like this, like an hourglass shape. This is part of the varicose mode. Now, at any given point on the interface, I can draw two radii. We have R1, and we have at this point again, I have another radius which is R2. So here delta P is gamma times 1 by R1 plus 1 by R2. And I also know one more thing, that since R1 and R2 are on different sides of the interface, 1 by R1 and 1 by R2 have opposite signs. I know this. We'll also confirm this mathematically. Okay. The interface for a shape like this will more or less will have the two curvatures on opposite side. You can think of several other examples, not just fluid interfaces, several other shapes which have this kind of a feature. Think of the saddle on the horse, right? The saddle on the horse has one curvature going this way and another curvature where the rider would put the feet going downwards, right? So it's a seat on the horse and you have two curvatures on two different sides. Okay. So let's start with calculating what is 1 by R1. 1 by R1 is nothing but 1 by, it is just the radius modulated. So it is nothing but R0 plus epsilon e power omega t plus I k z, right? It is, epsilon is small, so I can take it outside. 1 plus epsilon by R0 exponential of omega t plus I k z. This is 1 by R0 into 1 plus epsilon by R0 e power omega t plus I k z whole power minus 1. And now I can do binomial expansion and retain only the leading order terms, or only the linear terms. Sorry, what do I get? I get 1 by R0, right, minus epsilon by R0 square e power omega t plus I k z. I want you to remember that epsilon is has units of length because it's an amplitude of the radius. So epsilon by R0 square also has units of 1 by length. So this is an approximation. This is my expression for 1 by R1. What about 1 by R2? Now I can think of, just recall what we had done earlier in the free surface flow derivation, which said that if I have an interface like this, x and y, if I have an interface, arbitrary interface like this, which is defined as y equals h of x comma t, we define the curvature for this 2D interface as minus hxx by 1 plus hx square whole power 3 by 2, right? If the curvature is gentle, meaning the interface is varying gently, then this approximately is minus hxx, right? So in the same fashion, what you have now is you have this interface which is undulating, and at any point, what is the equation that we have? It is r equals, we have capital R of z comma t. This is the radial location r, right, of the interface. And therefore this is parallel, very similar to the figure that I have drawn on the right. I'll put that in a blue box. So just like y equals h of x comma t, here we have r equals capital R of z comma t. And if I use the same result for the curvature, we get the curvature in this case will be 1 by R2, and this will be nothing but minus del square R by del z square. And I'm ignoring the nonlinear terms because again we have the same issue. Epsilon is very small, so product of epsilon square can be ignored compared to 1. So therefore we have this. And what is del square R by del z square? This is nothing but minus, remember that expression for R is R0 epsilon, R0 plus epsilon e power omega t plus I k z. If I take the derivative of R once, I'm going to get an ik factor, and if I take it twice, I'm going to get ik twice. So I have epsilon e power omega t plus ikz times ik whole square. But I square I know is minus 1, and therefore I'm going to get epsilon k square e power omega t plus ikz. This is 1 by R2. So I have 1 by R1 and 1 by R2, and now I can substitute them into the pressure jump condition, the Laplace jump condition, which is gamma times 1 by R1. 1 by R1 we've already calculated. It is 1 by R naught minus epsilon by R naught square e power omega t plus I k z, and then plus 1 by R2, it's epsilon k square e power omega t plus I k z. This is the pressure jump across the interface. Now this pressure jump has two parts. This is delta P base state plus a delta P with a perturbation or a disturbance. Remember that even for a circular filament, which is undisturbed filament, because of curvature and surface tension, you actually have a pressure jump. What is the pressure jump in the base state? The base state pressure jump will simply be gamma by R naught, because the pressure inside is gamma by R naught more than outside, because there's only one curvature. It's flat in the axial direction, and in the theta direction it is basically having a curvature of 1 by R naught. So this we have plus a delta P perturbation. I'll just write it in shorthand notation. Okay, this is what we have. This will be nothing but gamma by R naught minus, what do I have here? I have gamma epsilon e power omega t plus I k z. I have taken these terms common. I have 1 by R naught square minus k square, and I can straight away cancel out the perturbation, the base state terms. You can also note that delta P perturbation is nothing but the pressure inside at R equals capital R, right? The pressure inside at R equals capital R minus the perturbation to the pressure outside. But there is no perturbation outside because it's just a passive gas which is unperturbed. And therefore I simply have P of R at R equals capital R. Again the same thing, P of R is the perturbation pressure, that is P of R at R equals R naught, plus you have the small terms. Small terms again would be, you have product of epsilon times del P by del R terms. This is again using Taylor series, right? So therefore I have P at P of R at R equals capital R naught is nothing but minus gamma epsilon e power omega t plus I k z times 1 by R0 square minus k square, right? We have already got the expression for P at R equals capital R naught. What is the expression for P at R equals capital R naught? It is minus rho omega C1 by K I naught of KR. Alright, I can substitute this. I have minus rho omega C1 by K I naught of K R naught will be minus gamma epsilon this is capital P times e power omega t plus I k z. This part is capital P of R. That is the definition of small p. Small p, the perturbation pressure. The pressure inside is capital P times e power omega t plus I k z. That's the normal mode form. This would be equal to minus gamma epsilon e power omega t plus I k z times this quantity. I can cancel the epsilon terms out and I have a nice elegant relation, which is rho omega C1 by K of I naught by K R naught is equal to minus epsilon 1 by r0 square minus k square. Right? So, we already know the expression. We have already determined one important relation, which is this kinematic condition. We'll call this kinematic condition as equation 1. And what does this kinematic condition tell us? It tells us the relationship between epsilon, omega and C1. So I can calculate C1 in terms of omega, and I can substitute this into equation 2. Okay. So I now have, using C1 from 1 into 2, what do I have here? So C1, what was the value of C1? C1 turns out to be epsilon omega by I1 of kr. Okay, and therefore I have minus rho omega by k C1, that is epsilon omega by I1 of k r naught. This is supposed to be r naught times I0 of k r naught. This is equal to minus gamma epsilon 1 by r naught square minus k square. Right? So again, epsilon is the amplitude. It does not matter. It should not also matter because ultimately we are dealing with a linear system. So the amplitude is arbitrary, and hence now I can put everything together and simplify to get omega square. So you have omega on the left hand side and omega square on the left hand side. If I write it as omega square, will be gamma by r0 square into 1 minus k square r0 square times k by rho, that's what I have, times I1 of k r naught divided by I0 of k r naught. That's what I have. I can do one more important step, which is I can multiply and divide by k r naught. I have omega square will be gamma by rho r naught cube times k r naught into 1 minus k square r naught square I1 of k r naught divided by I0 of k r naught. So this is called the dispersion relation, because it tells me the relationship between omega as a function of k, right, and other geometric parameters like r naught and material parameters like gamma and rho. So if I basically specify a filament of radius r naught, if I tell what is the filament made up of, what is the liquid, meaning its surface tension and density, then I can calculate the growth rate omega as a function of k. Alright. So we can also calculate the wave speed, or maybe we'll just come to this after analyzing this this dispersion relation. So this dispersion relation, if I take a few more minutes, so I can solve for this dispersion relation, right? So omega, as it turns out, simply becomes plus or minus square root of gamma by rho r naught cube k r naught times 1 minus k square r naught square I1 of k r naught by I0 of k r naught. Right? I have two solutions here, plus or minus of this. It's useful to remember what were we trying to solve. We said r of z comma t is r naught plus epsilon e power omega t plus ikz. So if omega is real and positive, we have an instability, right? Omega, real part of omega is greater than 0 if we have an instability. The flow is unstable. Let's see how does this flow actually look like. Let's make some sketches here of this dispersion relation. So I have k r naught. I want to plot the real part of omega here. I want to plot the imaginary part of r naught here. Okay. So the real part of omega naught, if you can clearly see this expression, it's for k r naught less than 1, omega is real part of omega is greater than 0. You have at least, you have two roots, one positive and negative. I will not go, the negative root actually does not have a lot of physical meaning, but I will not go into those details. But it's enough for us to know that we have a positive growth rate, which means that the flow is unstable. So where is it unstable? I basically can make a plot this way. So when k r naught is less than 1, so this is k times r naught is equal to 1, you have an instability. Let me try again. That's better. You have a growth like this, right? And we can also determine what is the value where you have the maximum growth. What is the value at which you have maximum growth? Omega r is omega max. This value turns out to be, we call it as k max times r naught, and this value turns out to be 0.697. Alright. So when you have two positive real roots, then you do not have imaginary part in this, but beyond this you have imaginary solutions here, which means that once you have k r naught greater than 1, you have oscillatory solution. So here you have, for k r naught less than 1, you have unstable region. K r naught less than 1, you have stable oscillations. K r naught greater than 1. Okay. So just to understand what is special about this k r naught, let's actually look at what is k r naught is equal to 1 condition. What does it mean? So if you write the wave number in terms of the wavelength, note that the wavelength lambda is 2 pi by k. So what you now have is 2 pi by k r naught should be less than 1 for instability. Let me just correct this thing. 1 for instability. We're plotting omega r, and this is omega I, the real and imaginary parts of omega. So we are interested in looking at regions where omega r is greater than 0, right? And it's real, and the real part is greater than 0. That happens for kr naught less than 1. And if I write it in terms of wavelength, we have 2 pi by lambda, okay, where lambda is the wavelength, and therefore I have lambda should be greater than 2 pi r naught for instability. Okay, in other words, a wave whose wavelength is larger than the circumference is susceptible to, is unstable. Okay, so this is a long wavelength instability. Any wave larger than this is unstable, but if the wave is actually smaller than this wavelength, then you would expect those waves to be, surface tension will not prevent those waves to grow, because surface tension is most effective at small scales. Okay, now what would happen to this instability as you let it grow? So typically what you would expect is, let's take a imaginary filament, straight filament. Now we have introduced a varicose perturbation on this. If we introduced a varicose perturbation on such a filament, this is an exaggerated drawing, but you can imagine that if the wavelength is larger than the circumference, or if kr naught is less than 1, such a wave would grow. Okay, and eventually what you may expect is that blobs of fluid would accumulate in these bulges. In these bulges you have blobs that occur, and fluid would move away from the troughs, and this leads to formation of the droplets. Okay, so you should expect that we can sort of make a guess that this wavelength will be something like lambda. This will be given by the wavelength of the perturbation that you have imposed. So we can actually do experiments where we impose exactly one particular wavelength, okay, through various mechanisms, either by basically adjusting pulsating the flow rate, or moving the needle up and down at a certain frequency, so that exactly a wavelength or desirable wavelength is introduced. Then you can actually precisely get this, test out this dispersion relation, and this has been done experimentally by several scientists, that this dispersion relation has been confirmed through rigorous experiments, right? So you can also ask, if I let this disturbance grow on its own, how long would it take to rupture? Okay, so you can make a rough estimate of the rupture time. Rupture time would be something like growth rate. Okay, and if I told you what is the value of where the maximum occurs, but once you substitute the value of kr naught is equal to 0.697, you can also get the value of the growth rate. Okay, and the value of the growth rate, if I remember correctly, is something like 0.34 times gamma by rho r naught cube. Okay, so that's the value of the, all I'm doing is substituting that most dangerous mode value. This particular wavelength is also called the, sometimes in literature you'll hear people say this is referred to as the most dangerous mode. The most dangerous mode is the mode which will grow the fastest. Okay, and so if you use the rupture time for the maximum growth, the rupture time will turn out to be something like 2.9 square root of rho r naught cube by gamma. But more importantly, it's important to note, I'm more than the number 2.9. I want to note that this is an order 1 factor multiplied by rho r naught cube by gamma, right? So there's a natural time scale that emerges if you were to do a dimensional analysis in this problem, and the natural time scale that emerges will be square root of rho r naught cube by gamma. This will just come by balancing the inertia to the surface tension terms. So all right, so I think we've basically covered the discussion of the Rayleigh-Plateau instability. Let me quickly summarize what we've achieved in this last few lectures. We have started with the stability of a stationary filament. We've linearized the equations. We've written down the normal mode form, and then we got an ordinary differential equation for the velocity, for the governing equations reduced to a bunch of coupled ordinary differential equations. We were able to combine all of those equations into one single ordinary differential equation, which is shown on your screen, and we were able to get the general solution of it. Then we applied the boundary conditions. The boundary conditions were applied at r equal to 0, and then we also applied 2 more boundary conditions. Why did we use 3 conditions? The reason we need 3 conditions is because we have to get rid of 3 quantities. Okay, we need one of the constants in terms of the other, right? We also want to get rid of C1 as well. So we want to get rid of both the constants and get omega in terms of k. Our goal is not just to find C1 and C2, but to go one step further and get the dispersion relation. So we got the dispersion relation. In this particular case, the dispersion relation turns out to be, I've put this in the box here. The dispersion relation turns out to be a simple quadratic expression. So omega simply depends on the value of the term that I'm highlighting here. This is a crucial term, 1 minus k square r0 square, because all the other terms in the dispersion relation are positive, and this term will determine what will happen to this entire right hand side. And remember, on the left hand side, because it's a square root dependence, this term will determine whether I'm going to get real and real solutions or imaginary solutions. If I get real solutions, I should always get complex conjugate solutions. And for me, that is enough to note that if I have a positive growth rate. And we can plot the dispersion relation. It basically goes from 0, the growth rate 0, when kr0 is equal to 0. And then when kr0 is equal to 1, the growth rate goes to 0 again, right? So beyond which we don't have any real solutions of this equation. We purely have imaginary solutions, right? So kr0 is like a critical boundary in the stability map. And physically what you should expect is, if you were to perturb the system precisely with that wavelength, then you should expect blobs of fluid to form in that wavelength, and this will be the typical rupture time. A small animation of a real simulation where we've done a small simulation where we took a filament and perturbed it by the most dangerous mode, and this perturbation grew with time, and you will see that it basically forms two separate blobs. You will see the simulation along with this lecture. Thank you.